Well, just in your what is written here. Okay, so what we want to ask a question about is like today we want to answer the question: Can the Oliver rate, can the Oliver information rate can be achieved? And that's a really good and deep question because it means can we in a way have after measurement have the same as before measurements about the optimality and do not lose anything? And so the answer will be um, a theorem which is called HSW, Holevo Westrauss method. So as we asked the question before, which was can is Holevo information can be additive, then we saw it is with entanglement breaking channel identity, and we went through entanglement breaking channel. Here we have the answer to the question: can the information rate be achieved? Which will be his answer with the theorem HSW that we will see together. So, in fact, I have three cases, um, and the case where it can be attained is like when you have conjoint measurements, joint measurement, and additive canal. So let's drive you through the three cases. First case, you separate separated measures at the end. So if you like separate, you measure like the first particle, after you measure the second one, after the third one, you have at the maximum the accessible information. Okay, so at the end, the max you can have is the accessible information, but it's inferior to the level bound because the individual measurements lose all correlation of the blocks. No, so if you have entanglement, for example, you'll lose it. You cannot see like the link between both because you just measure one after the other. Second case, the perfect case, is joint measurements plus additive canal. So it's like identity or entanglement breaking channel. So you measure all of it. But so at least in a way sends separated states, so row one or a two or a three, etc. The canal is additive, so yeah, the maximal we can have will be xn, and it will be this, and you joint measure, but there is no entanglement, so the entanglement at the beginning will serve to nothing, so you'll have literally the Oliver burn. So that's the second case, and the third case, like, so that's when we will achieve Oliver burn. Exactly, it's when we have joint measurement and additive canal, and third one is like joint measurements plus non-additive canal. So you preserve entanglement, and so you can even go further Oliver burn. So in a way, at least prepare some big entangled states on the row A1 to row AK canal, and Bob like realized like a joint measurement on all the block, but because the canal is not additive, we have like the Oliver Brown of all the stuff, which will not be equal, like superior to K of the stuff. Now, in the second case, it's additive, so it just k. Um, like in this case, it's superior, and so we will have c of n, which is equal to the limit of n of plus infinity of 1 over k, n is over k, which should be strictly superior to Holevo. So we will be superior to the Holevo information of a canal alone to really have the global capacity, the global classical capacity, thanks to the entanglement of the entries that still stay. So basically, to answer, yeah, we can have Holevo information that can be a Holevo bound Holevo information. Um, Holevo information rate can be achieved thanks to joint measurements at the reception. If the canal is additive, then it will be achieved, like it will be the maximal capacity, the absolute maximal capacity. If it is not additive, we can even do better by untangling at the beginning. In the case where it is additive, it's even like unuseful to untangle at the beginning. So yeah, that's it.